So you've arrived at the last video lesson before the Unit 1 test. And in this section, we're really getting more into integration. But this time, it's sort of the flip side of, inverse trig. The last time we talked about inverse trig, we, of course, talked about how it was developed and how to evaluate it, and also the derivatives. So what we're going to do now in this section is, if you happen to see an integral, and you happen to notice that the integrand looks like one of those inverse trig derivatives, then go for it and answer the question. And I guess what I'm trying to go with here is, like, keep in mind what an antiderivative is, or the integral of an expression is. That keep your eye on the prize, in the sense, like, what you have inside your integral, it's the derivative of some function. You just have to come up, hey, what is the function that I see inside here that has that derivative? So keep that in mind. All right, so what I want to be clear about in this section is we're recognizing the derivatives of inverse trig as my integrand. That's what I wanted to focus on. What I want to be clear of what we're not doing in this section is we are not yet going to actually come up with the antiderivative of arcsine itself. This is an unknown to us right now. I don't know what the integral of arcsine is. I'm not going to discuss that in this video at all. You're going to have to wait for Unit 3 for this. We will discuss it, but it is later. So I want to be careful when we say, hey, we're involving inverse trig. I mean, we're recognizing the derivative as our integrand, as part of our integrand. In the same light, I might as well talk about it now, because what we did in the last video is we recognized, the log rule for integration. And just to remind you what I'm referring to here is that the integral of 1 over x dx is the natural log of the absolute value of x plus c. What we did not tackle in that last video is we did not actually discuss, hey, what's the integral of the natural log function itself? We don't know that. We did not discuss it. We will not discuss it right now, but we will discuss it again in Unit 3 is where you get your really fancy, heavy-hitting techniques of integration. And so I just want to be clear about that. All right, now, here's our list. I like to see the derivatives with the integrals, so you clearly see this relationship, right? The derivative of arcsine is stated here, and what you're going to see in this section is this is the presentation of your work. Hey, what's the integral of 1 over the square root of 1 minus x squared? And that's where you're going to say, I recognize that as the derivative of arcsine. I'm going to go for it. Okay, so if you see these really nice setups where it's absolutely perfectly described, then go for it. You have your answers over here on the right. Okay, and that's pretty much what we have going on in example 1. It's not an exact layup, but it's as close as you can get to a layup. The only thing I did is put a 4 in that numerator, but that's just a coefficient. So, you can get around that issue really quickly just by taking that coefficient out. And then you've morphed it into a situation where, yes, the integral does look exactly how this is stated in this table. So again, you're going to say, I recognize, this thing in here as I see that as being the derivative of arctan. Let me just say it. So that integral is going to collapse to arctan. I'll slap a plus c on it and not forget about that coefficient of 4 that was hanging out. Now, when you look over at example 2, I changed the integral slightly from example 1 to example 2, and I just wanted to kind of capitalize on the sense of one minor change in an integrand can totally change your perspective or your strategy of what you're going to do. Me putting that little X up there, what I mean here by be careful is, as you move through this course, Calc 2, you get much fancier techniques. What I mean by the be careful is no matter how fancy you are, I always want you to consider, a basic straight up use substitution before you get into any of the more complicated structures. So that's just a general rule of thumb. You only do more complicated procedures when your regular rules tend to fall apart. Okay, so So me putting the x up here, now I'm going to totally abandon the inverse trig representation here because it's not an arctan derivative that I see in there. That x changes that. What this is going to be is a basic u sub where I'm going to let u equal the entire denominator, and you can see where we're going with this. Anytime you do that, you're trying to get it to some form of the integral of 1 over u du. So when you start with a basic u substitution, sometimes you don't really know how things are going to shake out. You just kind of do it and hope for the best, you know, and sometimes it'll work and sometimes it doesn't, and that's fine. I'm just going to go ahead and sort of translate this integral of what I was given in initially. You know, I had this 4x, and I decided to let that entire denominator be u, and I've got a follow through for dx now as well. And this is great. This is good news for me because I know I have some wonky coefficients to deal with, but in terms of this u substitution working, it certainly does because those x's are gone. So this is fantastic. And you've arrived at your goal, which is to convert this completely over into the integral of 1 over u du. Now I am going to loosen up the restriction. Normally it would be the natural log of the absolute value of u, but again, that 1 plus x squared is an expression that is never negative, so I can loosen up and I can curve out the 1 plus x squared. All right, so minor change in the integral changes your strategy, and so I want to always keep that in mind with all of these fancy things that you're learning because, you know, it's becoming really sophisticated. So listen, what we're going to do here, most of the time we're not going to see things that are like a layup, like example 1, where it's perfectly exactly the way the arctan derivative was defined. What your textbook has done for you is they've created a situation that makes it really nice, and you're going to do a little like mini u substitution in the integral to morph that derivative into the perfect form. I know that sounds like a mouthful. So we are still going to recognize, like, hey, what I see is kind of like an arctan derivative or kind of like an arcsine derivative, but I'm going to do a little bit of crafty maneuvering here with a like little baby u substitution to make it really pop out. Okay, so here's what I mean by the textbook. They did a lot of algebra for you here. They're really working it out. So if you have something other than 1 minus x squared, let's say instead of 1, you have a 16, right? Well, that's still a number squared. And let's say instead of x squared, you have, I don't know, 25x squared. Well, that's still a variable. I mean, the point here is that you have a number squared minus a variable squared. If you see that all under a square root, I can morph it into this arcsine antiderivative. Okay. If I see something arctanish, what I want to notice here about the arctan, see how there's no radical, and I've got a number squared plus a variable squared. Okay, so they've already done all the work here and sort of kind of toned that algebra to work out. Okay, what I see about the arcsecant, what I want you to recognize between arcsine and arcsecant, see how this has under the radical the variable part squared and then the number part squared. So it's reversed. Okay, remember with subtraction that order matters. So that's how I tell the difference between arcsine and arcsecant. Arcsine, I always think about it, hey, number squared minus variable squared. You know, it's not very sophisticated, but and it's under a radical. And then for arcsecant, what I'm looking for in my integrand is I'm looking for it to be variable squared minus some kind of number squared. Okay. And remember, arctan kind of sticks out because there's no radical. So I'm looking in the integrand and saying, hey, these look like they could possibly be derivatives of inverse trig functions. So we're going to make it work. So in example 3. You can kind of see I did mess with the same integral. Instead of putting the 4 in the numerator, like I did in example 1, I put it down there in the denominator. So instead of 1 plus x squared, I have 4 plus x squared. And what I want you to recognize here is this does sort of match the form of the antiderivative of arctan. I have no radical, and I have something that is, you know, number squared minus a variable squared. So that's what I really want to pick up on and capitalize on. All right, now it's not perfect because, you know, I have this other number other than a 1. That's why they put an A here. So here's how this is going to work. It's pretty crafty. I'm gonna recognize this as arctan, And I'm going to do this because I see no radical and I see a number squared plus a variable squared. What we're going to do is we're going to get in here. Maybe I'll just, I don't know, I'll change the color. I'm going to say, you know what? I recognize that. I'm going to say that a is 2. The reason I'm going to say a is 2 is because a squared gives me 4. Okay, so I'm just looking for a way to like make that work. Now what I'm going to do here is I'm going to say, well, what's u then? Well, u equals x. Okay, because if I square u, I would get x squared. And that's really, you're just kind of morphing it around a little bit using a and u. So you can kind of see we have a little u substitution. We are going to switch to the u variable, which means I still need a follow through. That's an important step. We can't forget about that. So what I'm doing is I'm translating this integral. Instead of the way it looks here, I'm gonna call it what it is. I said that a was 2, so I'm gonna write 4 as a squared, because, well, 4 is 2 squared. And then I'm gonna call that u squared, because I said that u was x. And I also have a nice swap out for dx. dx happens to be straight up du. So you have just sort of morphed that integral that was presented to you, and you've rewritten it in a way that kind of fits this form. So I can go right to the antiderivative. Like this is a straight up rule. It's 1 over a arctan of u over a plus c. And I'm going to reach back over here to say, hey, what did I say a and u were? Well, a was 2, and u was x. And you are done. So this is great. All right, you've got a nice antiderivative. Again, you do have a strategy of handling this. If this feels uncomfortable for you and you feel like, I don't know if that's right, you can always take the derivative of this answer here and end up with what you started. It's a little bit of an algebraic, conversion, but you can do it. Okay, you have a way of checking your work. All right, moving on to example 4, I've sort of created this situation here where, okay, I see this 1 over the square root of 9 minus x squared. A basic u substitution is not going to work here because you would need, like, if you think about letting u be that whole denominator down there, you're going to have a negative 2x kind of flying around and you have nothing to do to get rid of it, So a u substitution, a basic u substitution is not going to work on this. This is an integral that you would not have seen in Calc 1. This is definitely new material. So just kind of thinking about what I was saying here, u equals 9 minus x squared. This is your basic u substitution approach. You end up with something like this. And this is a problem for us because I have that x variable kind of hanging out and I can't get rid of it. Okay, so it's not a bad idea. It's not a silly thing to do. It's just something that doesn't work. So I'm going to abandon that idea. Okay. What I can do is realize, hey, I see something here that could be awesome. I see something that's arc sine-ish because I do see a radical, and I see a radical where I have like a number squared minus a variable squared. So I'm going to try to morph this into a perfect example of an arc sine derivative. And so what I'm going to do is the same little cute process here of saying, you know what? I know that I see that 9. I'm going to say that a is 3, and I'm doing that because 3 squared is 9, and that's the form I'm trying to match it to. I'm also going to say that u equals x. Now, I am sort of changing the variable of this integral, so whenever you change the variable, you do need that follow through, so I'm going to do that here. That's a really important step that a lot of people overlook. So what I'm doing here is I'm changing the way that this integral looks. Instead of saying, the square root of 9 minus x squared, I'm going to say a squared minus u squared, because that's what I have set up. And in place of dx, it's du. And now this matches perfectly what was in this chart up above, where it matches exactly to that bullet number 1. So I can kind of see here my antiderivative. Notice there's no extra coefficient of 1 over a here. It's just straight up arc sine of u over a plus c. So I am going to come over here and do that. Arc sine u over a plus c. Of course, I'll come in here and switch back to the x variable because that's standard practice. That's what makes sense. If that's the variable of your integral, that's what your answer should be in terms of. And so there is my antiderivative. So moving on to example 5, I sort of see the same setup in a way. I mean, I'm just sort of playing around with some of these numbers here. I see a 12 in the numerator. That doesn't bother me too much because I could just take that 12 out of the integral. That's fine. But I do, again, I'm gonna label this as being an arc sine-ish issue because I see the square root and I see a number squared minus a variable squared. That's what I'm kind of looking at there. How do I know which one to match it to, right? But I am going to kind of work on my little substitutions here. I'm going to say like, well, that's supposed to be a squared. Well, that means a is 1 because 1 squared is 1. And then I'm going to let u be, what am I going to let u be? U is 3x because if I square 3x, I get 9x squared. So once you set up a substitution and you're going to switch this integral over from x's to u's, I still need that follow through. So now, instead of writing dx, see how I'm going to have a swap there. It's going to be du over 3. That's a really, really important step. So try to highlight that because a lot of people miss that part. Okay, so I'm going to come over here and I'm going to work on what I have. I'm not bothered by the 12. I'm just going to take that out. That's more of a distraction. So I'm going to come here in the bottom and I'm going to say, all right, what do I got? Well, I said a was 1, so a squared, 9x squared. I said that u was 3x, so that I can call that u squared. And then in place of dx, remember, du over 3. This is my kind of switcheroo, and now I have an integrand that looks exactly like the arc sine setup. Now, I am going to combine the 12 and the divided by 3 and throw that outside the integral as a 4. But again, I have this perfectly matched up now, the exact form that I see, so I can go right to my antiderivative, which is going to be arc sine of u over a. And I guess, yeah, it's 3x over 1. I don't really need to write the over 1. I mean, you can, and that's fine. But I'm just going to say 4 arc sine 3x plus c and be done. Okay, so we're kind of like recognizing the integrand. With a little bit of work, we can manipulate it to be a perfect inverse trig derivative form. Okay, that's what we're doing. When I look here in example 6, I do not see the right order. I see a square root, right? I want to try to label this, but this is not an arc sine. I'm going to match up to an arc secant. The reason I'm going to do that, I do see a radical, so it's not arctan, but I see a variable squared minus a number squared. So that's how I know what to match it to. My goal here is to match it to an arc secant. And let me just kind of slide. I'm going to kind of fly up here. I'm really going to try to match the integrand to this setup. And you can kind of see how weird it is, right? There's a u and a square root of u squared minus a squared. I don't see that in my integrand yet, but I'm hoping I can make this happen. I'm hoping with the right u and a choice, I can make it look like that. So I'm going to go ahead and get started. I know where I'm going to go with this. And I'm going to kind of work this out. I'm going to say that u, what is u going to be? Well, this is problematic. See, 2 isn't a perfect square, but that's okay. Don't lose your mind. I'm just going to say u is the square root of 2 times x. If I square that, I would get 2x squared. So this is great. I'm going to say a, again, 5 is not a perfect square. No problem. A is the square root of 5. They can be ugly and unfriendly, and everything is just fine. Now, when I'm making this switcheroo, keep in mind I still have my follow-through happening here, and I still have a legal swap of what I'm going to replace dx for. Dx is going to be replaced with du over root 2. Okay, let me come at this and let me, recreate this integral. What I'm saying here, I'm going to put a 1 over here. 1 over, I have that x. I haven't addressed that extra x on the outside yet at all. But I can say that 2x squared, as I've defined it, is going to be u squared. Minus 5, I'm going to say that that's a squared. And then remember my substitution here for dx is going to be du over the square root of 2. So I'm kind of like almost there what I want you to see here is this x and the root 2, and how do those things sort of work themselves out here? I want you to look at that. I want you to put those together right down there in that denominator. And what I want you to recognize is that that actually is you. That's legal. I have actually achieved my goal of making that integrand look perfectly like this generalized form of the arcsecant derivative. It's kind of a mouthful there, but you have done it. This is great. So what I'm going to do is go right to the antiderivative, because I've got 1 over a. I'm going to have arcsecant of the absolute value of u over a plus c. And let me kind of throw in these issues that I have. I said that a was root 5, got it. I said that u was the square root of 2x. And I think this is lovely, but I don't know. Maybe the answer key that you're looking at has rationalized version, right? If I just multiply top and bottom by root 5, I get root 5 over 5. I'll do the same thing over here. I'm going to multiply top and bottom by root 5. That would make this root 10. And that looks great. Okay. Okay. Now, again, let me just kind of come back at this. We're sort of like dealing in this section of, recognizing inverse trig derivatives as our integrand. Let me just be clear about this problem in and of itself. Let me just change colors. Maybe I'll change to brown. I don't know. If you were to kind of try a basic U substitution, I just want to show you that it fails. I don't want you to think, it was a silly thing to do, because I actually always want you to consider it. But if you were going to do a basic U substitution, you'd be going back to your premise of like, hey, let U be everything inside that radical. And your follow through would involve a 4x. Okay, so what does that do to my work? Well, I would end up with, basically have a 1, I have an x, I'd have the square root of u, and then my follow through would be du over 4x. So you can kind of see, like, this is why I didn't do it this way. Like, that u substitution fails here because, I still have extra x's down there. All right, so sometimes it's just good to regroup and take a look and see what happens. When you're taking the Unit 1 test, you might do this. I don't think this is bad. You just put a line through it, right? So I just figured I'd address that. Okay, here we are with example 7. Okay, and I think maybe I'll end the video here and just kind of restart, since I'm already at 20 minutes or so. And I'll do another video to tackle these other guys. But these are your base models for recognizing inverse trig derivatives in our integrands.